Hello everybody, welcome to today's episode of iCANX. And today we're going to have a really wonderful afternoon. My name is Christian Nijhuis from the University of Twente, and I think most of you have seen me before, so I will keep the introduction of myself very short. Last week we had a very super nice talk from Marcus Antoinetti from the Max Planck Institute of Colloids and Interfaces. And of course, today we are all here to hear Damien Thompson from the University of Limerick. This is today's team. I'm the moderator. We have 3 panelists that will, after Damien's talk, ask interesting questions. We have Yuan Lee, Ivana Lin, and of course, the one and only Alice. But let me introduce you today to today's speaker. Well, Damien Thompson and we go back a long time. I think we met already back in 2010. And since then, we have, I would say, a most wonderful collaboration. Me as an experimentalist, I'm always amazed how Damien always picks up the most complex concepts and really can turn it in easy to understand language. Really wonderful. Well, Damien is a full professor of molecular modeling at University of Limerick. And besides that, he is also the director of the Science Foundation Ireland Research Center for Biopharmaceuticals. And there he leads basically the modeling activities. He is not just doing modeling, he is modeling molecular dynamic simulations, DFT simulations, but really everything from big biomolecules to small memristive type of molecules and electronic devices. So his scope is just unbelievable. So herewith, I would like to give the floor to Damien, and I'm very much looking forward to hearing your talk.
Thank you, Christian. Let me just see if I can share my screen.
Yeah, I can see it, and I can hear you clearly.
Great. Okay, so thank you very much, Chris. Thank you very much for the very kind introduction. To paraphrase Ben Johnson, my mother would have enjoyed it, or my mother would have believed it, and my father would have enjoyed it. So thank you. It was great. So today, and it's also a great honor to be here. I love these iCANX talks. I often go to them. I often go to the videos to get a quick tutorial in the latest research and materials, and they're really excellent. So it's really, I feel very honored and privileged to be part of that legacy and that group of speakers. So thank you very much for the invite. So today I'll be speaking about predictive modeling of bio-inspired materials, and I'll stick mainly to molecular electronics. As Chris mentioned, in my group, we do a broad range of activities with a lot of different collaborators, and we bring that central piece of molecular modeling to those collaborative projects and in many different areas, but today I'll speak mainly about molecular electronics. So we're a group of computational physicists and computational chemists who develop new methods. So as Chris mentioned, that can be molecular dynamics, can be DFT, quantum mechanics, and we are very much inspired by our experimental collaborators in that we often get dared to invent new theories and new ways of coding things as required. To figure out nuances in spectroscopy and microscopy. So we develop the codes and the techniques that are needed to really push forward fundamental science. So it's a very privileged and a very stimulating environment, I think, to work in. And I've been very lucky with the group members I've had. We're a very diverse range of people. As human beings, we tend to be very different, which of course makes it fun. But we are all united in that common love of science and that love of figuring things out. So we're both scientists and engineers, I would say, by mindset. So we developed those new methods and with a focus on using those methods to help develop advanced materials in partnership with our experimental partners. And that can be academics, it can be industry partners. We have a broad set of collaborators that we work with. And when we're lucky, sometimes those advanced materials even find their way into energy efficient electronics and sustainable technologies. So it all rests on quantum mechanics. So for those of you who, unlike me, haven't spent the last 20 years studying this stuff, this is probably what you remember about quantum mechanics from your undergraduate days. So you have Schrodinger's cat, which is both dead and alive. And that's what the maths tells us. I mean, you see Einstein and Feynman are laughing here. And Feynman also said, shut up and calculate, which I love. So it's stop worrying about, how can it be that way, and stop trying to see the world through our lens of big lumbering creatures, and just accept that if you're an electron, you're very small and very fast, and your physics is very different to what we think of as everyday physics. So thankfully, we have quantum mechanics to guide us. So we have Schrodinger's equation, which tells us that this Hamiltonian, this energy operator, acts on the wave function that gives us out a packet of energy levels that correspond to different allowed energy levels of the molecule, or if you like, molecular orbitals. So that wave function tells us the location and the velocity of the particle. So we get out the rungs on the ladder in which the electrons sit. So we go from just having a three-dimensional picture of the molecule, an X, Y, Z coordinate for each atom, to actually being able to describe where the electrons are in the molecule. So that's incredibly powerful because it tells us about polarization, it tells us about bonding, it allows us to actually predict the properties of that molecule. So in a nutshell, that's what we do. And of course, it's a very seductive notion, because you get the idea that you can just predict everything. So no more, going to the lab and sometimes sleeping in the lab and trying 17 experiments to try and get to the answer. You can just get the right answer, first of all, on a computer before you ever go to the lab. Does that work? Well, sometimes it does. Not always, obviously. So it can be a tall order to actually incorporate all the complexity of the experiments in your simulation cell. So thankfully, I work with some very good experimentalists, and I'll embarrass our host, Christian Nias, by saying he's by far the best of them. He's an incredible experimentalist. So I know when I work with people like him that he knows what's in his beaker. And if he can tell me exactly what's in his beaker, then I have a shot at actually getting all that complexity in the model. It's not always successful, but at least he knows what he has in his system. So I have a shot then at actually replicating the molecular formula of that in the computer. So the idea is we get the structure that's from X-ray crystallography, it can be from NMR, it can be from structural homology. There's many different ways of generating that 3D map of the atoms in the system. Then we put that into our supercomputer, we calculate the dynamics. If we believe statistical mechanics, and we do, if we can calculate the wiggling and jiggling of the atoms, that gives us a shot then to predicting the properties of the system. So we can do rational design. So what I'm talking about here is using it for design of high density, ultra low energy digital computing. So essentially using big computers to design even better computers. So there's kind of a circular logic there. And we're not necessarily making bigger computers, but more energy efficient computers. So as we go towards Internet of Things, as we go towards digital computing, there's a massive unmet need to make computing materials from sustainable materials, and also materials in which we can control their thermal properties. So we can actually achieve these high density computing platforms that don't go on fire, essentially. So that's where our materials design comes in, to try to work a little bit smarter there, try to simplify the components that we use. And it's similar to actually the way we were designed by evolution. I mean, as you simplify, often you optimize as well. So that's kind of a central theme of what we do. So we have our structure, we calculate the dynamics, from that we get energetics. So that allows us to predict the stability, say, of alternative forms of materials, and we have a shot at then predicting what types of materials and what the material phases are going to be produced in the lab. So as chemists, we're interested in this because we're interested in making new materials. As physicists, we like to make new devices, and depending on what day of the week it is or who I'm speaking to, I can be a chemist or a physicist. I sit very happily in both worlds. And then the piece that I miss, and where I rely a lot on my friends, is to actually develop new technologies. And to be blunt about that, the best way to do that is befriend electrical engineers. So people who actually know that world, which I certainly don't, but how to actually design, miniaturized circuits, how to optimize those and actually get the best performance from your materials. So if you like, we design the materials, and then we have the electrical engineers who get the best possible electrical signal, electrical properties from those materials. So computers can help us here. We can bridge this gap between, if you like, knowing and doing. So having knowledge of the system through structure, dynamics, and energetics, and then actually making things, making new materials, making new devices, making new technologies. Because computers can go where experiments find it very hard to go alone. So for example, we can put numbers on nanoscale physics. We can predict binding of molecules to surfaces. We can predict the stacking and packing between molecules on surfaces. We can even sometimes predict charge transport through molecular tunnel junctions. So these are things which, this type of information is very useful to help to understand experiments and even ultimately to guide experiments. So we can control the structure at the nanoscale through our blueprints that we get, through the design rules we get from our computer simulations. we can design useful structures, because we know again from statistical mechanics that if we control the structure, we control the function. So there's a very definite structure-function relationship at the nanoscale, which we can encode in our modeling programs. So we do multi-scale simulations, and almost everything we do is in partnership with experiment. So this example here, and of course, typically because I'm presenting this live, the little movie isn't working. And this is a rule, I think, of scientific presenting, that it always works in the rehearsal, but never when thousands of people are watching. What you should be seeing here is this molecule. So it's a single molecule nanostructure. It's a little gold nanoparticle with a dendrimer wrapped around it, and that dendrimer is fluctuating and wiggling and jiggling, as all molecules do, at temperatures above 0 Kelvin. So we can come up with these types of designs, these types of, say, single molecule nanostructures to be used as components in miniaturized circuits. But often, we struggle to actually capture all the complexity of the system in our model. So sometimes, our beautiful idea doesn't make it to fruition. So part of that is just that natural gap between theory and practice. So it can be difficult for us as computational modelers to capture all the complexity of the experiments. We call ourselves predictive modelers, but sometimes we're actually struggling to keep up with the experimentalists in terms of capturing what's in the experiment. So what can help us with that? Well, first of all, we can always use bigger and faster computers. If you look here at this league table, this latest strapped to the top 500 for supercomputing, Ireland is in position 16, which isn't bad actually for our small island such as ourselves. We're usually not in the top 20 internationally, so we're not doing too badly. But that equates to like a 1% system share of high-performance computing. If you look at the people at the top here, unsurprisingly, that's China and the US, and together they have over half the system share of HPC in the world, of high-performance computing in the world. So it's more than an arms race in that, the bigger your computer, the faster you get the answer. There's also a lot of other factors involved, but just in terms of brute force, you can get the answer faster, possibly, in China or the US than we can in Ireland. So how we do is collectively, we work through international networks so that collectively we can be internationally competitive. So that means iCANX is the Irish Centre for High-End Computing. We partner, say, with the UK, which is the Archer system. Through Europe, we are initiatives such as Euro HPC, HPC-QS, where we can actually pool our resources. And many times my students are actually computing on supercomputers, say, in the Netherlands, or in Germany, or in France. And for us, it's just a login screen. Sometimes we don't even know actually where in the world our calculations are being performed. So they get sent through various data streams to different high-performance computing networks throughout the world. So I would say in the last 5 years in particular, a lot of the access to computing has been much more democratized now. So anywhere in the world, I would say, you can actually get access to these very, very large supercomputing centers. And usually you don't pay for it. Usually it's on a, you apply, you write a grant proposal. And if it's interesting, if you're pushing forward the state of the art in scientific computing, you have a good shot at actually getting time on these very large machines. So if I can be brave and make a prediction, I would say that within the next 5 to 10 years, with advances in hardware and software, I think we can realistically expect to model full biological cells with atomic resolution, and maybe even watch their assembly from scratch from a soup of component molecules. So as well as the thermodynamics, we also have a shot at actually calculating the kinetics of how these things happen. So we're getting very sophisticated. I say this is the entire community. We're getting quite good at actually modeling self-assembly from scratch. So rather than relying on X-ray structures, cryo-EM, spectroscopy, we can actually just start with a bunch of molecules. And if we sample for long enough and we capture the environment correctly, then we can actually spontaneously watch the emergence of structure in our simulations. Michael Feg in the US is one of the leaders in this. For example, here we see how you can actually model quite large parts of cells. So you have full atomic resolution here, and you get these beautiful Monet-type paintings of cells. So you've got all your proteins in there, your membranes, your metabolites, all interacting with each other. And you can get a lot of information on how macromolecular crowding works, how to actually target individual sites in cells from these types of simulations. And if we move then to what's becoming possible in terms of scale, with the best high-performance computing systems, we can sample for out to milliseconds. So that seems like a short length of time to us, but when you're sampling, when your time step is 1 femtosecond, so the breathing of a carbon-hydrogen bond, that's an awful lot of structural snapshots that you go through to get to 1 millisecond. So that gives us a shot then at actually reaching experimental timescales for things like protein folding, allosteric transitions, cellular signaling, and even actually, well, ultimately out to the cell lifespan. In terms of size, we're at the stage where we can realistically model, say, proteins and even viruses, where we're getting to the point where we can model actually small living creatures such as bacteria or organelles inside human cells. So just in terms of brute computing force, we're getting there with full atomic resolution. And also we have lots of tricks. So we can do, say, coarse grain modeling, where we neglect some of the fine details of atomic structure so that we can get, a more qualitative model of very large systems. We've also, my group has been actually done a lot in this, developing accelerated sampling methods, whereby rather than just starting at time zero and letting the system, evolve deterministically, there's these tricks you can use to actually jump around in the potential energy surface and try to get a full measure of the Boltzmann population of different substates within that system within an experimentally or within a reasonable computational time. So I'm telling you this as a way to just show the power of high performance computing and how we're taking advantage of the ever increasing capability of both hardware and software, and how we're applying that to very, very challenging systems such as cells. The other things we need to get right as modelers are, say, a better understanding of entropy and viscosity. You'd be surprised when you actually look under the hood of modeling codes how much is still very much fuzzy, I would say. So every year or so, I get a very smart maths and physics graduate here from the University of Limerick and give them a really hardcore PhD project in actually, coding up viscosity. And they have, depending on the student, that can be, an awful lot of fun. And you can never assume that the code does everything right. It's always worth actually questioning, especially if you get funny results. It's always worth actually looking at the original coding and see what you can do to improve it. Some of the codes are quite old now. You're talking like 20 years old. So there's always room for improvement. Another thing we need to work on is statistical analysis. So, I mean, it's kind of a joke in the field that we always assume our simulation box is large enough because that's the only one that we can afford to do. So when, we get a new high performance computing system and we can suddenly go from, say, a system with 1,000 waters to one with 5,000 waters, we generally find that what we assumed didn't make a difference actually does make a difference. So it's always worth actually, going to larger systems, doing replicates, trying to get a better statistical analysis of our systems. Generally, we get the right answer qualitatively, even with modest computing resources, but to get really, really high precision, say, in binding free energies, it's certainly worth going to very, very highly accurate systems. And also the better link with experiment. So a lot of the fun that I have on a daily basis is actually trying to figure out wiggles and jiggles in, say, a Raman spectrum. And, the devil is in the details. So we can really make, and I'll give you some examples of that in a few minutes, we can really make significant progress as we look deeply into the fine details of, say, how molecules breathe inside molecular devices, looking at, say, very subtle motion of counterions in molecular devices, and trying to then resolve, fine details of spectroscopic signals using DFT calculations to really understand the mechanisms by which these devices work. Because they're so small, even a difference of a single atom, or say, I'll show examples where we go along the halide series, we go from fluorine to iodine, and the properties change dramatically. So it's something we don't get in, macromolecular engineering or macro scale engineering or macro scale science, this absolute critical dependence on single atoms on device performance. So if you think of it in terms of, time scale and spatial scale, this box that we have allows us, even with modest computing resources, to sample quite easily for microseconds for systems out to about 100 nanometers. So the little box here is quantum mechanics. So that's where we do the really, really accurate calculations. And then once we have those done, we understand the bonding in the system, we understand the polarization of the system, we understand what the atomic charges are in the system. We can generate classical models for the molecules and then subject them to molecular dynamics, which allows us to access much larger and much longer timescales. So we can model things like, say, drug carriers, molecule cell interfaces, large area films and crystals, and antibodies using these types of fully atomic scale resolution simulations. So what? So, that's nice. That's nice philosophical argument. Professor Thompson, thank you for that. Modeling is great. But, what do you use it for? So I'll give you some examples of that. So first of all, I'll very briefly just explain why it's difficult, and that's design rules for nanoscale engineering. That takes like 30 seconds. Then for the rest of this talk, I'll talk about examples of where we've used it. So the first one is molecular scale 1D, 1R resistive RAM. And the second one is a ternary memristor created by a charge proportionation. So in a nutshell, we try to make the things for the Internet of Things. So as digital computing continues, as AI, as Internet of Things progresses, we need better computing. We need smaller components, we need more functional components, and we need more real estate, per centimeter squared on our chips. So how do we do that? And molecules is one obvious way of actually increasing the functionality of your circuits, of your miniaturized circuits. So the first design notes for nanoscale engineering. Why do you need computers? Well, it's because little things are weird. As we scale down to nanoscale, as we scale out to molecules, surface area becomes critically important. So things that we care about at the macro scale, like friction and mass, aren't so important at the nanoscale. Because we're going so small, see, little things really are weird. Everything becomes dependent on surface area. So things like van der Waals interactions, which you don't think about in everyday lives, that sticking of molecules to each other becomes critically important. And they're the types of things that we can calculate using our molecular code. So we can calculate electrostatics, we can look at hydrogen bonding, we can look at van der Waals interactions, those steric interactions between molecules, we can look at covalent interactions. So we can look at those nanoscale interactions using our computer simulations and relate them back to experiment. So if you think of it in terms of what types of materials we can look at, for example, organic, inorganic interfaces, which I'll concentrate on today, are critical for molecular electronics, for neuromorphic computing. And also we have things like organic interfaces, which are critical if you want to design, say, pharmaceutical co-crystals, or you want to look at piezoelectricity in, say, peptides. So as I said, for today, I'll concentrate mainly on organic, inorganic interfaces and molecular electronics. So the simplest example I can give you of that is this SAM-based molecular tunnel junction. So these quite tuggish looking molecules are alkylamines. So they're assembling on graphene. And this is the simplest experiment you'll ever do. It's just a sheet of graphene. You get and Chris can tell you that you've got a beaker of alkylamines, you pour them on graphene and they do this. So they spontaneously do this. It's self-assembly. There's nothing, there's no finger of God coming down telling these molecules what to do. You're not relying on any kind of chemical interactions. You're not pumping energy into the system. They just do it. So the alkylamine will bind, the head group there, the NH2 group will bind to graphene through just weak dispersive interactions. And the molecules stand up and they stick to each other using just very, very weak van der Waals interactions between these methylene groups. So you get these beautiful monolayers forming spontaneously on graphene. They also do it on coinage metals like, say, silver, gold, or platinum. And if you stick a top electrode on there, then you can make a molecular tunnel junction where you can actually transfer charge from one electrode to another through these molecules. So that's the basis of these types of devices. So here's Chris again with his group in Singapore. So we asked, can we do more with less? And I've been working with Chris now for well over 10 years, and this is some of our most recent work as shown here. So I'll concentrate mainly on the electric field driven dual functional molecular switches and tunnel junctions. So can we actually make 1D, 1R? Can we have a component which has both the resistive memory and the diode, or the diode in one place? So can we get away with actually a very, very small voltage drop across that multifunctional component? And the answer, of course, is yes, otherwise we wouldn't be telling the story. But I'll tell you how we did it. So these types of new types of multifunctional molecular scale switches, they're important because they reduce the footprint of devices. You get more functionality in a smaller space. In turn, that lets you decrease the power consumption in your nanoelectronic circuitry. And most critically, it enables new functionalities. So you've got this bridge into soft robotics and neuromorphic computing. You can go places where silicon can't go. We'll never replace CMOS. That's not our job. But these types of devices, these components can go where silicon can't. So for example, for wearable electronics, for mimetics of the human brain, for memory-centric neuromorphic chips, we can develop these types of miniaturized circuits based on molecules that can perform new, interesting properties. So here, we want to replace the current high footprint, high power, resistive, random access memory, or RAM solutions that use two types of switches combined in series. So that's a current rectifier, or a diode, and a resistive switch. So you might imagine as a computational chemist, I then screen, millions of different molecules and ask myself, okay, which one of those would make a good candidate for a next generation, one diode, one resistor, or RAM? And that's an incredibly difficult question to answer. Instead, what we did is we went to literature. So armed with these parameters, we knew from the experiments the switches must be stable. They must be reversible, they must be writable, and they must be addressable in the solid state. So that's quite a tall order, and not many molecules will do that for you. But luckily we found this guy. So this is Biogen, methyl Biogen. This is from a paper about 10 years old from Yu and Marcel Meyer, where they showed that these Biogens form lovely, stable, uniform, self-assembled monolayers on gold. And they also exist in two redox states. So your Biogen group can be +2 or +1. So it can be a dication or a radical cation. And using that switching, you get interesting properties. So we tried that. And from that, we achieved that unprecedented dual functionality of diode and variable resistor in one component. The device properties are astounding. I take no credit for this. This is all Chris's work, but just to tell you why we were so interested in modeling this and why it's so important to actually understand the mechanism of these things, they work unbelievably well. Chris is Dutch, so he'd never say that. He'd say they're quite good, but trust me, this is absolutely state of the art. So the current rectification ratio is 10 to the 4. That's pushing up against the lower limit of CMOS, and this is with molecules, which are 2 nanometers thick. And you also get a resistive on-off ratio of about nearly as high, so 6.7 times 10 to the 3. And all of this is done with a sub 1 volt drive voltage. So generally for devices, you're talking about 2 to 6 volts. So you're getting a massive energy cost here because the potential only drops over one junction. So that new type of electric field driven molecular switch, it operates in a tunneling regime, as I'll show you, that enables a new class of molecular devices where multiple electronic functions, we've got 2 so far, but there's certainly room for more, and they're pre-programmed inside a single molecular layer. So that's a thickness of 2 nanometers. So that's 10 to 500 times smaller than other devices. So you're getting the new functionality and you're getting it in a much, much smaller area. So how does it work? Well, our results, which I'll take you through, they indicate that the switching relies on dimerization of redox units. So if you like, the molecules pair bond, like penguins, humans, uniquely among the animal kingdom, but they form these lovely pair bonds. They stick to each other in pairs. And that results in hybridization of molecular orbitals, and that's accompanied by directional ion migration. So that idea isn't new. I mean, our cell membranes do that all the time. Our transmembrane proteins rely on directional ion migration, but to date, it's been very difficult to show that the controlled directional ion migration inside synthetic, molecular devices. And that's what we showed here. So here's the system. As I said, the methyl Biogen has different oxidation states. The ground state is a dicationic +2 state. So that's stabilized by these X- guys. These are counterions. These can be perchlorates or chlorines or fluorines. There's lots of different ones you can use. As you bias it, then it cycles through different oxidation states. For example, the radical cation +1 state, and in the fully reduced form is the 0 state. So there's your mobile counterion here. So as I'll show you, the stability and the functionality of this junction relies on the controlled motion of this counterion from here to here. So it cycles between the head group and the bottom electrode. So here at negative bias, we can see that the molecules dimerize. So you take advantage of that pairing of the electron spins on each of these radical cation units and a pi-pi stacking between these aromatic groups. And that coupled with the migration of the counterions provides charge stabilization required for resistive bistability. In a nutshell, that's why these devices work. It's why the molecules don't burn up, and it's why they can perform and continue to behave as very reliable electronic components across multiple cycles. So we can see we can write the equivalent circuit here. It's the same as 1D, 1R, Rm. So the diode rectifies current and with high rectification ratios. So that's our IRR is equal to JV over the corresponding charge density at negative bias. And that's coupled with our variable resistor. So at high on, we achieve these high on-off ratios, this R2 versus 1 between high and low conductance states of the junction. And they're provided by formation of that diamond. So we can track this using CV. So Chris's group had these beautiful spectroscopic signals where we can actually see, as we bias, the formation of these different redox states. So here you see reduction from +2 to +1. And down here, you can actually get this signature for the formation of the dimer. And here from our DFT calculations, we can see that. We see the pi-pi bonding HOMO and the pi-pi star anti-bonding LUMO. So this is the symmetric and anti-symmetric combination of the highest occupied orbital and the lowest unoccupied molecular orbital on these monomers in the dimer. We find the dimer is always formed, both from the experiments and the simulations, irrespective of the nature of the counterion, with the switching behavior, the properties, the electronic properties that you get And the junctions, they depend critically on the counterion size. So every counterion can do this trick, but not all of them do it as well as each other. So we see here, and again, this is the experimental data. This was the best signal, I think, that Chris got. This is with the iodide. You see this large unipolar hysteresis, only at negative bias. And from that, then you can extract out your current rectification ratio, your resistive on-off ratio, and that sub 1 volt drive voltage of 0.9 volts. So that's the best operating device, and that's achieved with iodide, which is the largest diameter of the halides. I should say here that these beautiful fits were achieved by Cameron Nickel, who was a PhD student in the group of our friend Enrique Del Barco in Florida. Cameron's now moved on. I'm glad to say he's still working with us because he's basically a genius, and he can do amazing things with analytical modeling. So the black data points here are Chris's experiments, and these red lines are the fits. So it's fit with Londo theory, but Cameron in his genius can actually make these fits using a remarkably low number of free parameters. So this really helps us to understand the mechanism of the junctions. So the challenge then in obtaining stable and efficient electric field driven switchable molecular junctions is to fine-tune that stabilization of charge on the molecule. So I think that's the bit that was missing in previous work. How do you actually keep the charge on the molecule under extremely high electric fields? So as you bias this, you go to electric fields on the order of gigavolts per meter. Not many molecules can survive that. And it's, as ever in life, it's a Goldilocks effect. So you want to be just stable enough. If you've got unstable on and off states, they just naturally, lazily fall back due to thermal relaxation. But if you've got overly stable states, then, for example, those that you create using covalent bonds, they result in impractical, slow switching speeds. So you want fast switching, but you also want something that's very, very deterministic and very reliable. So here's the device properties. You can see you get these very, very reproducible read-write, read-erase pulse sequences. You get very, very good output and persistence of output across multiple cycles. And yeah, you get current retention for long times. So the devices work very, very well. Here's what they saw when they switched to the smaller counterions. So if we go to bromine, then chlorine, then fluorine, you still get the behavior, but the electrical properties decrease quite drastically very quickly as you go to smaller counterions. Chris is a very good experimentalist, so there's a lot of controls. So for example, if you put in perchlorate or PF6, these are larger counterions, the thing just stops working. Likewise, if we exchange for salts, like ammonium chloride or this sodium carboxylate salt, nothing happens. So we need the halides, and we need, for the best device performances, we need iodine. So why is that? So we scratched our heads about this for a long time. We had a lot of Skype calls, a lot of emails. It was a very good lockdown project, and it distracted us from the world being on fire, and we just talked about molecules, which is always very good reasons to do science. It certainly kept us entertained and kept us occupied to try to figure this out. So eventually, through a lot of calculations, I tried lots of different ways of actually calculating the stability of these junctions. And after a lot of thinking about it, and after a lot of trying kind of progressively more silly things, I came back to a very, very simple metric. So just the formation energy of the dimer. As you go from monomers to dimers, what stabilization energy do you get? And we see here that we get by far the largest stabilization with iodine. So we looked at that. We used molecular dynamics and DFT calculations to look at, as these dimers form in the presence of different counterions, what kind of energies do we get? So for fluorine, it's repulsive, it's positive energy, so it's very, very difficult to form the dimer. As we go to chlorine and bromine, it becomes more favorable. It's most favorable at iodine. And again, as you go to larger things like PF6 or perchlorate, it again becomes less favorable. So we're very happy with that. But I generally never believe one modeling result. So then I thought, okay, what's another way of doing it? So I used a different, this is just what this looks like. So here's the junction of different states, and we're cycling the counterions from on top down to the bottom electrode. So that they instead of going off into space, these counterions actually land at the interface between the molecule and the bottom electrode. So they're trapped there and they cycle back and forth. We think that's what gives you the stability of the device. So in these models, that we always did that. We always moved the counterion down here to balance the charge. So we get this trend, which seems to agree with experiments. But then we thought, okay, what's another way of calculating that? So a completely independent way of doing that is just to actually calculate the total energies in the on and off state. And I was absolutely thrilled to see exactly the same thing. So then we started to actually believe that okay, that could be a rationale for why iodine works so well. So it's allowing, it's basically the motion of the iodine is allowing the dimer to form more efficiently, and it's allowing the system to cycle more cleanly between the on and off state. We then thought up a control simulation where we forget about this cycling of the counter ions between the head group and the electrode and actually allow the counter ion to escape into vacuum. When we did that, we lost the correlation with experiment. So we get this near linear correlation between the size of the counter ion and the stability, which doesn't agree with the experiment. So they're the control simulations using alternative hypothetical on state that's shown here, in which the counter ions are not allowed to migrate down to the interface. So that proved, well, it certainly supported that hypothesis that this oscillation between the head group and the bottom electrode is what's crucial for actually creating this high performance, highly stable device. Then we can go as ever to our energy diagrams and we can see how the charge transport works in the system. So here we show coupled charge tunneling from the bottom electrode, from the top electrode to the bottom electrode through the available energy levels in the molecule, and that's coupled with ion motion. So we get electronic motion coupled with ion motion. So it relies, for this to work properly, we need this controlled transfer of the counter ion from the head group to the bottom electrode. Also from our DFT calculations, we can get out, say, maps of the valence electron density in the system. We can see where the electrons are moving around. We can plot the electrostatic potential through the junction. So I've turned it on its side here. This is the gold, this is the top of the molecule. And we can just, from that electrostatic profiles trace, we can work out the work function shift in the junction. So we can get a lot of information on how the electronic structure of this type of junction actually leads to the observed electrical properties. And we also found this curious correspondence actually here between the resistive on-off ratio and this parameter that we pulled out. So this is the stabilization energy of the dimer divided by the energy offset of the HOMO as measured from spectroscopy. I think it's fair to say, Chris, we still don't understand why that is, but we love this straight line. And if anybody listening can actually have a sensible idea of why this is, I would absolutely love to discuss that in more detail. I won't wave my hand about it, but it exists. This correlation exists. And yeah, we have our energy diagram, which allows us to understand how the device works in both the on and the off state. So we've negative bias and positive bias, and we see the shift of the HOMO level depending on which counter ion we have. And we, as we say, we see this linear dependence on the size of the halide. So we like this. This is molecular design. It's showing how very, very subtle differences in the architecture of the device, in the ingredients of the materials in the device, has a huge impact on the observed electrical properties of that device. So yeah, this is a summary of it. I think the important things are, yeah, we get the very, very high performance. We get a low drive voltage. We get it with a very, very thin layer. And I think it shows how we can simplify device structure and associated fabrication. The key design principle, which we worked out from a lot of spectroscopy, a lot of electrical measurements, a lot of DFT and molecular dynamics simulations, is that we fine-tune that balance between stability and switchability. So again, it's a Goldilocks effect. You want it just stable enough, just switchable enough. So that was achieved here by optimizing the size of the counter ion, because when you optimize the size of the counter ion, you optimize the diffusion of the counter ion through that molecular tunnel junction. Okay, so that's one example of controlled ion motion. So the time I have left, I'd like to tell you about another related example. This is done with a group in Singapore. This is the group of Shritosh Goswami, who now has his own group in India. And he was working at the time as a PhD student with Venki Venkatarajan. We also have people like Jens Martin, a lot of clever people working on this project. So the idea here was to try to develop new types of memristors. To relate back to the previous work, I would say it's keep copying nature, see what other new types of miniaturized devices we can create using that trick of controlled ion motion. So we know from transmembrane proteins, from synapses, from neurotransmitters, controlled ion motion is incredibly important. So can we, as nanoscale engineers, nanoscale designers, can we come up with synthetic analogs which perform similar tricks? So that's what this work is about too. So here are the architectures that were built in Singapore. So we have different, it boils down to, this is the active layer. I'll show you the molecules in a minute. This is ruthenium with two redox active ligands attached to it in the metal organic complex. You've got ITO underneath, and you've got some type of gold above. It can be a flat electrode, it can be nanoparticles. You can even use gold nanocrysts. And we see exactly the same signature in terms of memriscence for all three structures. What scales is the actual values you get for current density. So depending on the device engineering, you can actually really increase the current densities that you get, but we get exactly the same signature for all these devices. So that tells us that the signature that we're getting depends on the nature of this molecule, this ruthenium complex. So the conductances of these three film states, which we call 0, 0, 1, 1, and 3, 1, you can see here they're separated by large orders of magnitude. So you get these very distinct addressable conductance states. That's very, very important if you want to make devices. You want these distinct energy levels or these distinct conduction states. So the curious thing about this molecule is that it gives you that. You get a very, very large energy gap between the different electronic states. So they can be switched from one to another by application of threshold electrical voltages. So you switch with three distinct conductance plateaus as shown here. So to try to explain this, we looked at permittivity measurements, which were incredibly informative because they show that the lowest conductance ground state, that 3-1 state, has the highest permittivity. So you get this big spike in epsilon, the dielectric constant in the ground state. And then that decreases rapidly with increasing field, and it switches sharply here at V1 and V4. So those transitions between 3-1 and 1-1 are very, very sharp. And they are accompanied by this massive change in permittivity. On the other hand, if we look at the lower oxidation states or lower redox states between 0, 0 and 1, 1, we get noticeable change in permittivity at the other switching thresholds. So that's at V2 here and V3. So something funny is happening at that, doubly charged state, that 3-1 state. So we try to understand that electronic state. Just to say, as well as being a resistor, it also acts as a MEM capacitor. So we get this dual function as well in this device. So it's both a MEM resistor and a MEM capacitor. I might come back to that. So here, if we look at the energy states, we have state 0, 0, state 1, 1, and state 3, 1, well separated in terms of conductance. Try to understand that, we use spectroscopy, and we map out these different vibrational modes for the molecules. The molecule is shown here. This is our ruthenium. It's a metal organic complex. We have these azo ligands complex to it. These benzene groups, a very, very simple molecule, but the key to it is that you've got these azo groups, these N double bond N species, which are bound to ruthenium. So they hybridize with ruthenium, and you get these very, very distinct electronic states whereby the azos can either host 1 or 2 electrons. And again, just like before with the system with Chris, we've got mobile counterions, and here they're PF6s. So they move around within the organic film, and they stabilize different electronic states. So if we look from the Raman, which is incredibly informative, as I said, you get these vibrational modes at around about 1300 wave numbers. You see this state 0, 0, very, very marked state. Then as you go to state 1, 1, you get this additional peak, which we call E1 at about 1260. And then when you go to state 3, 1, so this is the doubly redox state, you get a third mode. So this mode around about 1185, which we call E2. So they're assigned to the stretching and the breathing of these azo groups in different redox states. Okay? So here at E0, all the azo groups are in the same uncharged redox state. And then in state 1, 1, an additional E1 mode becomes active. And that's shown here. The DFT calculations are shown here, where that's spread over the azo groups with some hybridization with the central metal. And then when you go to 3, 1, you get this third azo mode coexisting with the two. And that's the curious one, because it doesn't match the solution state spectra. So if you look at here, if we compare what we see here from the film UV-Vis spectra, we get none of these match the solution UV-Vis spectra. So that tells us that we've got something curious here when we actually do the 2-electron reduction. We don't have a symmetrical electronic state, which confounded us and confused us. And again, it certainly occupied me very happily as a modeler to try to understand this. So what we concluded from the spectroscopy and from the DFT, and I'll show you the DFT in a second, is that 3-1 state does not have all the pairs of molecules doubly reduced, but instead it has pairs of triply and singly reduced molecules that stabilize a broken electronic symmetry. So that's the charge disproportionation state. In solution, this would never be stabilized, but in the film, due to actually stabilization of the supermolecular dipoles by those mobile counterions, you have this unusual state in which that charge disproportionate state actually becomes thermodynamically favorable. So if we look again at the spectroscopy, UV-Vis spectroscopy in solution, we see the state 3-1 matches perfectly with 50-50 average of the solution state spectra of the triply and singly reduced molecules. So that gave us that cartoon of the system whereby we've got one molecule in a triply charged state and one molecule in a singly charged state. So we don't get pairs of doubly charged molecules. So here from the DFT, we see these, this is 1, this is 3, 1, and 3. So we get this highly resistive and high capacitive state here. And that's our ground state, our 3-1 state for the doubly charged system. And here at the singly charged system, we get all the molecules are the same. So this, if you like, this structural and electronic inhomogeneity gives us this unusual charge disproportionate state, which gives us access to these new memory levels in the molecule. So if we go back again to our permittivity, we can see we can explain that from a coexistence of differently charged species in the 3-1 state. So that gives an abrupt change in permittivity during that transition between 1-1 and 3-1. And the formation of the supermolecular dipoles, which we map through the simulations, that results in a larger film permittivity compared to the other Redox states. So you've got this, if you like, if you imagine a pair of molecules, you've got the electron, the electron density, the overall electron density smudged over the two molecules is being shifted or pointed in one direction. So the counterions have to assemble themselves in the film to compensate for that. So you get this stabilization, this counterion mediated stabilization of that asymmetric electronic state. Okay? So here's the DFT. So we saw here, if we compute the energy difference between this non-charge disproportionate state and the charge disproportionate state, we get a very, very small energy difference in, a perfectly crystalline film. In this case, actually, the non-CD state wins by about 100 millieVs. But if we allow the system to become a little bit disordered, so we just simply expand the unit cell of the crystal a little bit, and we allow the molecules to move a little bit, we allow the counterions to move around in response to charging, then we see a very, very, very clear difference in energy. And in this case, the 3-1 state becomes thermodynamically stable. And we know from the experiments that we don't have a perfectly crystalline layer. And it's actually interesting from the simulations to suggest that if we had a perfectly ordered single crystal, the device wouldn't work. So it relies on this small degree of amorphousness in the system, or a slight degree of structural disorder. Actually, gives enough wriggle room in the film for the counterions to adapt and move around in the system in response to the device. So the DFT calculations predict the stabilization of that 3-1 state only in that expanded cell. So that gives us some insight into what's happening in the experiments. And if we look then in the expanded cell, we see the counterions. This is the expanded cell. This is probably it's hard to look at the first time you see it, but here in green is the normal crystallographic positions of the counterions with respect to the molecule. And here in blue is what happens in our simulations where we allow them to move. So we get this, it's a sub-angstrom change in distance. So it's a very, very small controlled motion of the ions, but that's enough to stabilize that state, that asymmetric state. And we see that then from the displacement, we see, we get like 0.3 angstroms. Motion is enough to stabilize that charge disproportionate state. Okay, so that's great. That's DFT. And in a roundabout way, it supports the experiments. But certainly, I still wasn't happy with that. So I went back to Shritosh and asked him for smoking gun evidence of ion motion. And Shritosh, being an incredibly talented experimentalist, gave it to me. And that's this. So you get this plot of energy. So KT, so the minimum temperature for complete formation and transition to and from that charge proportionate state, as you go to very, very low temperatures, you get this perfect correlation with the inverse of the size of the counterion. So that confirms the role of that thermally activated counterion dynamics in charge proportionation. So you only get access to this asymmetric electronic state when you allow the counterions to move. So to summarize then, the field-driven redox transitions in our films enable the realization of a single device that can be interchangeably used as a binary or ternary memristor, a binary mem capacitor, or even both concomitantly. So we know from the electronic properties or electrical properties that we get the signature of a mem capacitor as well. So we get two devices in one, if you like. And that's it. We explain the energy levels that we see based on our DFT, which support the idea of a charge disproportionate state. So the aim of the work is not to produce an industry standard product. We certainly were not able to produce a mass producible device just yet. But this multifunctional device, the realization of it, the proof of the fundamental science that it works, it offers new opportunities for the design of ultra miniaturized circuits. And I know Shritosh is working on, say, crossbar architectures, which can also be used to make these look more like actual real circuits that can be used for digital logic and storage that are being further explored. And also, very interesting from my point of view, films can be deposited on soft and curved surfaces. So you don't have to have a stiff planar substrate. So that opens up then also, routes to ubiquitous memory and computing, maybe wearable electronics. So you can layer them in multiple layers and they can adapt to the substrate, which to me is very interesting. So I'm almost there. In terms of where do we go next, I would say as computing hardware improves, as the software improves, we have a shot at actually making full quantum dynamic models of organic assemblies on adaptable substrates. So actually modeling that full, using the looking at the electronic structure, looking at the molecular structure, how it evolves over time as we look at, say, bendable or flexible substrates. So one fabulous application of that I could imagine would be coupling external switching and motion for soft robotics. Also, another activity in my group is developing unified physics-based predictive models for energy harvesting. So, what we talked about here has been miniaturized electronics, but how cool would it be if those components were actually self-powering? If we could have, autonomous power sources for these components, maybe we can deploy them in edge computing. So that taking advantage of their natural tendency to actually generate voltage themselves in response to squeezing or in response to conformational flips could actually be a way to lower the power consumption, or even have them as their own power source for future applications. Also, I would say something as a community, as a field, we should look more at design of alternative, sustainable, biocompatible molecular materials in our miniaturized electronic devices. So the more we can get away from rare earth materials, the more we can, use things like peptides, green chemistry, if you like, in our devices. That certainly helps us with integration with biology. And then it opens the door then to applications, say, for pharma and medtech applications. So, I mean, in terms of the SDGs, Sustainable Development Goals, hopefully you've seen that what we've been talking about, it hits very much, good health and well-being, as well as affordable and clean energy. And I would see those as being really central grand challenges for our community, because once you take care of those things, you also impact on things like poverty, on sustainable cities, on quality of life, on environment. So I think it's profoundly important that as a community we move towards more sustainable, more high performance materials, because they can have a very, very dramatic impact on the materials and technologies that we use in our everyday lives. So hopefully I've convinced you that computers are fun and useful. That was my job here today. So I thank obviously my group. The alumni are shown here, also my current group, and I'm privileged and honored and very lucky to have a fine group of experimental collaborators which keep me well motivated. And thank you all very much for listening, and I'm very much looking forward to the panel discussion and addressing any questions that you might have. Thank you very much.
Absolutely fantastic, Damien. Really wonderful presentation. Thank you very much. Okay, let me share the screen again. So then we go to the panelists. So let me introduce you first, Yuan Li, who is now an associate professor at Tsinghua University. Well, we also go back already quite a long time ago, because he did his PhD in my group from about 2010 to 2015. And he did really extremely well. But before he joined my group, he got his PhD degree from Zhejiang University in 2008. And he got his master's degree at the University of Eindhoven here in the Netherlands. And if I remember correctly, that was with Alex van Herk. After he completed his PhD studies in the National University of Singapore, he was for 3 years in a group of George Whitesides at Harvard University. And in 2019, he then moved back to China and started his new group. Then today it's really a close-knit family party, because Ivana Lin is now at the University of Twente. Actually, she's sitting literally, the door next door. So it's really a privilege to have her here. Ivana graduated from Oxford University with a specialty of electrochemistry, and did a PhD with Professor Jeremy Baumberg at Cambridge University. And she joined University of Twente just last year in 2022. And I think she's really well recognized for her pioneering work in spectral electrochemistry. I think one of her major achievements is that she could detect a chemical reaction as small as 8 molecules. That was published in Nature Catalysis a few years ago. And she could even detect single molecule metal bond formation and made the world's smallest plasmonic pixels. And the last panelist, or the third panelist, maybe I should say, we don't have first and last in this community, we have only members, is of course the one and only Alice. And I think as a founding father or mother of iCANX. I think she really requires no further introduction. So let us have maybe for the next 30 minutes or so the questions. And I think as it is now being set up to have the bench ready with all the panelists, I think I would ask or invite Yuan Li to start the discussion. Please go ahead, Yuan.
Okay, thank you for the introduction from Chris. Yeah, Damien, thank you for that wonderful talk. I really enjoy it. I have few questions. Maybe I start from so Chris asked me to start, so just let me to. So I will ask my first question will be you have mentioned that for the computer you can computer, for instance, model layers or sometimes a few molecules, but sometimes can be enlarged to bacteria. That I can consider bacteria have many items. But for quantum physics, so how that can be achieved to actually realize to calculate for instance the bacteria in this large size, what compromise you need to do, or there's some resolution you need to sacrifice, or what?
Yeah, so I mean, if you want to get very accurate energies, if you want to get the binding free energy to 1/10 of a kcal per mole, then you certainly do need the full atomistic modeling for that. You don't necessarily need quantum mechanics. You can do it with classical mechanics as long as you've got a good force field to describe the charge distribution in the molecules. But yeah, you do need to do fully atomistic resolution simulations. They're called free energy calculations, essentially, where you would morph, if you like, alchemically mutate the molecule from one state to another and see how strongly it binds to say a surface or another molecule. But then if you want, so then for that you would have to, you would have to necessarily have to just cut out a piece of the system, so you get the biological interface. Remember, I mean, electrostatic interactions, the tail, it takes a long time for electrostatics to decay, but after about maybe 2 or 3 nanometers, they do tend towards zero at least. So you could cut out, a segment of your very large system and encase it in a box of water and do your very high resolution atomic resolution simulations on that. The alternative is to try to actually have more of the system in there, so to take account more of the extended environment, whether that's a biological cell or whether that's, say, a liquid interface, whether it's an amorphous film on top of some sort of a conductive substrate, whatever the system is, and you want to get more of the extended environment, then yeah, you can go to, say, you could use a united atom approach, or you can go to completely coarse-grained modeling approach, where you would lose some of that atomic resolution. So use bead models. So for example, the simplest example I can imagine is for a protein, instead of having all the atoms, each amino acid is its own bead. So for example, say aspartate has a certain radius and it's negatively charged, lysine is a different radius and it's positively charged. So then you sacrifice a little bit of the quantitative predictability, but yeah, you can certainly look at larger systems. So we do things like, say, we would use a coarse-grained model to try to say, so okay, so for example, we get a cryo-EM model of a very complicated biological interface. We can use coarse-grained model to simulate that entire system, say that entire organelle or whatever it is. And then from that, so we push it out, say, for a few milliseconds, and we try to simulate a little bit of molecular dynamics in there. We might try to trigger allosteric transformation or something inside the protein. Then from the snapshot that we get, we can then go back and fill in the full atomic structure, then take out a piece of that and do our very high level calculations on that. Does that answer your question?
Yeah. That's
so
good. So
why
I want to
low
ask,
resolution, complicated, to high resolution, less complicated models.
Yeah. Why I want to ask, one of the reasons is that I'm also in my group developing a complicated biological interfaces to study not only charge transfer but also energy transfer. So yeah, so I'm.
So what do you look at, say, micelles, or what kind of biological nanostructures do you have?
Yeah, so we are actually not only the protein model layers, but we try to observe not only on the metal surface, but also we want to observe them on lipid bilayer surface, and also we want to add more protein, not protein, so enzyme then those multi-enzyme catalytic system. Yeah.
Yeah,
So
because it did occur to me, I mean, I know your recent work that I didn't speak about today, but the paper
yeah.
just published in Nature Communications, where you bend the gold substrate and you get this, you know, you have this, the adaptability
Yeah.
of the monolayers. You could simulate macromolecular crowding in there quite easily, actually.
Yeah.
You know, because as you go to the concave structure, you're forcing maybe proteins to get a little bit closer than they would naturally do. Through just free energy relations. So yeah, that we should speak more about that.
We should, yeah, definitely, yeah, definitely. About later, about send you a long email actually. Yeah. Anyway, let's continue to ask. My second question is about the biology system, right? The biology system is about so to achieve this high on-off ratio. So there's ion migration, right?
Yep.
So this is actually quite general question because I really know the detail of this technique. So a general question is ion migration for memory resistor is it's a good technique to generate memory resistor, but at least what I know from people who actually working on memory resistor from physics or electrical engineering, they said ion migration maybe not the best mechanism to do that because they always have at the end you will short your devices. So they are actually trying to develop phase changing system. So for a theoretist, normally you can predict those materials. Any idea you have can share with us and the audience?
Yeah, so I think I know the work you're speaking about. So it's the migration of the iron through the, it's not quite filament formation, but it's large scale motion of the iron. So here, remember, we're talking about that they're only going down the length of an alkyl chain. So it's, you know, it's 2 nanometers. So when we say migration, it's basically shuttling of the ion through just up and down the chain. So it's a very different scale to what would traditionally be ion migration in memory resistors. So I would say to model, and I know some people have done this for the large scale motion, it would be even probably a coarse grain molecular model would not be sufficient. You would need some sort of analytical model for that. So you would fit it through to a diffusion equation essentially, and try to somehow get the topology of the interface in there. So you could incorporate defects and try to map out the topography in a quite coarse-grained way and measure the diffusion coefficient through those different mazes, if you like, or those two different types of structures. But there will be very little molecular resolution in there, I would say.
Yeah, but
I'm also problem. You're moving a point charge through a maze. That's how I would model that, I think.
Yeah. And that maze actually dynamic, right? So because some molecules are vibrate and some are attaching the surface, they can transfer ion, some are not, but they are neighbors. So
for us to transfer, I mean, if you think of it, modeling is often presented as a continuum. So you have your quantum mechanics, your molecular dynamics, your analytical models. And so what we would compute down here at the realm of, say, microns and milliseconds would be diffusion coefficients and sticking probabilities. And then we can pass those two parameters to more analytical models, computational fluid dynamic models. So then we can take those as single just values, but they are informed from the molecular motion. So as you say there, the molecular motion is important, but by the time you get to, say, a CFD model, all you would have is a sticking probability and a diffusion coefficient. So they would reflect in a coarse grain way the molecular structure of the material.
Yeah. Okay. Thank you for the detailed answer. My last questions for the last part. So just actually a very small detailed technical question. So I think what you model for the last one for the charge dispersion system. So your model is I think in a crystal, right? Well, a crystal, right? But I think that is a molecular film for the real device. So and the devices should have some boundary or defects or it's definitely a polycrystal, I guess.
So you're right. What we see, I mean, certainly they're very, very reproducible, the electrical properties. So they're not critically dependent on. There will be defects, but they don't seem to be critically dependent on them. But what's important ingredient seems to be the fact that, you know, they're not perfectly packed single crystals. It's a semi-crystalline film. So the only metric we have to measure that, it's kind of like a radial distribution function between the rutheniums. So you can get the average distance between the metal centers, and it's a little bit larger than you'd expect if it was perfectly crystalline. So we know they're a little bit spread out on the ITO substrate. So that little bit of give in the system seems to be important to allow sufficient, entropy, if you like, or conformational freedom of the molecules to adapt to those different bias states. So if you want to stabilize the charge disproportionation state, then you need somehow to push the counterions around so that they actually stabilize that new supramolecular dipole that you're making. That's the idea of it.
Okay, yeah, thank you. Yeah, I think I keep some time already, so let's maybe continue, and later we can discuss more. Yeah.
Thank you for your
Yeah,
question.
sure.
Yeah.
So before I'll hand over the word to Ivana, let me say to the audience, please, no matter where you are, no matter where you're listening from and looking from, if you have a question, just put it in the chat box, and then I'll introduce it to the speaker. Please type in also your name and where you're from, so then I can speak it out loud. Okay, Ivana, the floor is yours.
Thank you, Chris. Thank you, Damien, for the wonderful talk. You have shown very successful modeling to see how molecules interact with the electric field and undergo redox, and then using the simulation to tell us the underlying mechanism. So protein is new to me, so I wonder how about combining protein and Raman spectroscopy? Because for me, I think it's like a big molecule, so it's complicated with all the geometry and say intermolecular interactions. So can you tell me, introduce a bit more about these fields, please?
So you're asking about Raman spectroscopy on what types of materials?
Like protein, like big biomolecules.
Yeah, for protein. So yeah, you're right. It's extremely difficult to get clean signals from them. So that's where simulations can help, because we can decouple that, and we can identify vibrational states of particular subgroups in the protein, for example, ferritin or chlorophyll, these large complex multi-protein assemblies. Yeah, we have some shot at actually measuring, say, the flexibility at particular protein-protein interfaces, and then seeing the vibrational states that we compute. Can we map that onto the experimental data? But you're right, it's incredibly challenging for something like a protein. It's very difficult. When we talk about Raman for biomolecules, it's usually peptides that we speak about rather than full proteins.
Let's see. Thank you. And my next question is about combining optical field with electric field and molecule. So so because I'm a spectroelectrochemist, so I've seen how powerful it is to combine the electrons and the molecular orbital. But then in the recent few years, we got asked by the reviewer on the papers a lot that, okay, why your DFT model doesn't consider the optical field? The answer is there is no current tool available. So for example, chemists, we use DFT, we use the molecular structure to predict the vibrational spectra, and physicists, they have say FDDT modeling to find out the optical field, but then there is no bridge between them. But fundamentally, I believe they both use the same electronic structure of the molecules, so like permittivity. So I feel like there should be some way to merge. So I wonder, what's your opinion in this, in terms of interdiscipline simulations?
Yeah, no, it's interesting. It's a very interesting question. I know that. I mean, I know the work of Jeremy, and he worked with Javier Esperoa in Spain, an incredibly talented modeler. And yeah, you're right that currently we don't have that. Someone should write an ERC on that. That's something that the community needs to actually directly couple the photonic response. Yeah, it tends to be done. It's broken up into two pieces. Yeah, so somebody looks at electronic structure, somebody else looks at the photonic side. And even when I think of modeling groups I've worked in over the years, it tends to be the electronic structure people, the photonics people, and sometimes it's kind of it's a language difficulty in some ways. And often, as you get to know people, you realize that you're actually calculating the same thing. Everything boils down to the band structure, the density of states, vibrational states. And yeah, more communication between those fields is important. Chris and I and Enrique organized a conference a few years ago, which had a very, very long name. It's in my office. Yeah, so Molecular Electro-Opto Spintronics. It was one of those SPICE conferences where we tried to bring together all those people, and that was a fun few days. Yeah. So yeah, you're right. There's a need for that. The physics is not so different, but it certainly hasn't, to my knowledge, and it hasn't been coded up properly in a single software that you can actually do that. And yeah, that's a good idea. And somebody maybe ourselves can do something about that. Yeah, great question. Thank you.
Yeah, and my last question is, because you have so many projects in parallel, like from your own group and also from collaborations, maybe can you share your tips on how you can manage so well on so many things altogether, also for maybe our audience, bachelor, master's, PhD students?
Oh, I mean, just drink lots of coffee and sleep 4 hours a night, and you may what you can do. No, I'm kidding. I mean, no, that's what you do as a postdoc. It's certainly what I did as a postdoc, but it's not sustainable. It really isn't. Eventually, you hit a wall, and you don't know what's too much until it happens. You know, and it's actually a danger in science, because we really do. We reward people who take that deep dive and, you know, go down a very, very deep hole. And I must say, it works. I mean, if I've made any big discoveries or any progress that I've made, it's been through that deep dive. It's from the, you know, 3 o'clock in the morning, you suddenly make the connection and everything makes sense. And I don't know another way to do that. I wish I did. I'd love if you could, you know, work diligently from 9 to 5 every day and you would get the same result. I'm not sure that you would, but I think we have to, as full people, as humans who are scientists, we're humans first and scientists second, right? So, I mean, there's an opportunity cost there. So if you find yourself, you know, staying up till 4 o'clock every morning writing code, there's an opportunity cost. Possibly, you know, your girlfriend will not want to talk to you anymore. Maybe your family won't speak to you anymore. So yeah, sorry, it's getting a bit silly now, but you know, you absolutely have to prioritize your time. And yeah, there is a tendency to let science consume you. So I would say, for me, the way I do it, and maybe it's not the most healthy way to do it, but it's kind of you know, in cycles. So there's times when I will really take a very deep dive. Now, I mean, I'm a husband, I'm a father, I've got 4 little children at home, so I'm not allowed to behave like that crazy postdoc anymore, but I'm allowed to do it sometimes. So, you know, you have the times where you really are, you know, this week, you tell everybody, this week I'm going in, you know, I'm going to, Johannes given me this new challenge, and I need to develop a brand new type of modeling to do that. And, you know, I won't be accessible to you for a few days, and you take that deep dive. And yeah, that's how I do it. But then I certainly cannot do it all the time. I mean, so it's an age thing as well. Obviously, I'm in my 40s now, so I cannot do the really, you know, continuous all day, every day, hardcore deep dive that I could before. So sorry, that's probably a complicated answer, but I would say be careful, mind your mental health, mind your time. And again, as you get older, you learn how to prioritize. So, you know, you learn that, you know, you've got your, you know, the papers that you absolutely have to get out before Christmas, and then the other ones, which maybe you can leave until January or February. So it's prioritization, I suppose. That really, it's been a long road for me to learn that. But yeah, in a nutshell, I would say prioritization. So work hard, but for a purpose. Make sure that you're prioritizing things which are most important. And that can be something that works towards a medium-term or a long-term goal. So don't just answer the person who's, you know, bugging you the most. Think about what's most important for you in terms of what you want to discover and how you want to build your career, and structure your time accordingly.
Thank you for your experience. That's all for my questions.
Thank you again.
And of course, when you have young children, you think you have finally your break, and then your 4 or 5 year comes to you and asks, why?
Yeah.
Why not?
And you realize
why?
you know nothing. Yeah, you're a fraud. Imposter syndrome kicks in then. Why is the sky blue? No idea. But you know, those conversations are also the things that make life worth living. So there's more to life than science. And it took me a while to realize that, actually, but it's an important thing to realize. For all you young people
thanks a lot. I think we all recognize that. Yeah, but I think cycles and having good breaks is really key. Alice?
Yes, I'm here. Yeah. Actually, I think I'm one of people studying chemistry here. So I have some questions for them. Yeah, you give a beautiful, pictures and beautiful results for these materials simulations. All these kind of results are really exciting. So as engineers, I'm thinking about. Did you think about the fabrication or mass fabrication? Yeah.
So that's the part where I say, to be successful, you befriend talented electrical engineers. So that's not my world. It really isn't. I enjoy speaking with people about it, but I mean, I guess my world is the molecules. So it's down at the nanoscale, and it's looking at the molecules. And then I guess I rely on my collaborators then to array those materials in such a way and to, you know, to electrode them in the right directions to maximize the response from the materials. Certainly, we can trace that to the nanoscale. I mean, for example, in our work in piezoelectricity, we figure out where the supermolecular dipoles are in molecular crystals, and then that gives us some clues about if we want to make devices, the direction along which we electrode. So where we make our electrical contacts is actually very, very important for optimizing the electrical output from those devices. So in some cases, yeah, we can trace from the molecular to the macro scale. But when it comes to actually fabrication, device fabrication, no, I'm lucky that I've got some very, very talented friends who know all about that.
Okay, good. Yeah. So like you say, that's a collaboration word, you know, the people need a big support from other fields. So I see, Damien, in your talk, you say that you have some talented students from mathematics, you know, some from that. How you deal with these kind of different peoples? I know that many mathematics students even speak a different language. Yeah. So how can get all these people working together?
So yeah, it's a big. I mean, as the director of the research center in pharmaceuticals, as Chris mentioned, I mean that's my job every day is to actually bring people together, and it's a very difficult thing to do. It's much, in some ways, it's much easier to write code and look at molecules and interact with each other than human beings. But I guess, I mean, what I've learned is that people are motivated to work together when they have common challenges. So you think of an overarching challenge in sustainability, or in, you know, energy efficient electronics, and then because you will have people, you require a multidisciplinary approach to actually tackle those things. No one of us by ourselves could tackle such a large challenge. So then you assemble your team, and you assemble the different pieces of the puzzle. And yeah, it's difficult because even I'm sure Chris could also attest to this. When we publish our papers, if we have, like, you know, many different PIs from different fields, it can be very difficult to even find reviewers for those papers because they're so multidisciplinary. And sometimes it's very difficult for any one of us to hold the entire work in our heads, you know. But for me, that's incredibly motivating and stimulating. And, you know, it certainly drives me to bring my A game in those types of situations. I mean, definitely my favorite thing to do is to brainstorm with people from different areas and to try to figure out, you know, what the common goals are, and also how to relate to the physics that I get and the outputs that I get. How is that actually useful to, say, device engineers, and how can we make those meaningful connections? And I would say it's a lot of talking. It's a lot of meetings such as this, you know, whether it's online or whether it's in person, and actually trashing things out. Sometimes the whiteboards are very useful. And just the brainstorming together. That's how we do it.
Okay, great to know that, you know, dealing with the peoples, you know, always talking with different ideas to try to get some, you know, common challenges to figure out.
Yeah, I think so.
Yeah. So Damien, I have another question follow up with this. Yeah, you see that you have such a large group, you collaborate with many different places, right? Yeah. So if you met someone really challenging you, always say no to you, how you deal with that?
I love that. I mean, I say that to my students on the first day. If you always agree with me, then only one of us is necessary. And guess which one that is. I mean, if you want to be here and you want to contribute, then you have to disagree with me. Otherwise, what's the point? I mean, and you find, I mean, I remember myself when I was an 18-year-old student. I mean, you nod and smile, and you think the professor knows everything. So I really encourage my students to challenge me and think. And I'm lucky in that there's some visibility now for the groups, and certainly for postdocs, I get people coming in from different fields, so they bring that knowledge with them, and they learn from me as much as I learn from them. As much as they learn from me, I learn from them. So yeah, I love to have students in the group who necessarily will not have done molecular modeling as their mainstream. So people from different branches of chemistry, physics, mathematics, engineering, even biology. And that brings fresh ideas to the group. And certainly it creates very stimulating group meetings. And I mean, the one rule of my group is that you're not allowed to pretend that you don't understand something. So if you don't understand something, you ask, and we thrash it out together. There are no stupid questions.
Damien, how nice you say that. Actually, I ask this question for, you know, all these students. Please be brave enough to say no to your professors, right? Yeah. Please brave enough to challenge your professors. This was the new things come out. If you always, you know, follow your professor, agree with him, there was nothing new, right? Yeah. So thank you very much for your comment on this. Chris, as a chair professor, how did you deal with this?
Yeah, I couldn't agree more. I also have the most fun when you get a question and then you realize, hey, shoot, we actually really do not understand that. And that is where the most excitement comes out. And then when you have something very fundamental, you can also make that biggest impact. But before we close up, I also have a question about myself. It's something you said in the beginning during your introduction about that you can really now model quite reliably supramolecular systems, and even just from the very building blocks, you can predict what structures they will form. But I think that is very complicated because the environment they are in, even the solvent they are in, just simply changing the solvent can give you a completely different outcome. So that is basically my question. I know often in talks, now I also realize it myself, usually the focus is very much on the molecule, or how it sits the molecules on the interface, and what are the geometries, the binding geometries, the tilt angles. But actually the environment plays an equally important role. So how do you capture the environment? How do you model environment?
So everything.
For instance, in my brain, I do not understand interfacial water even.
Oh no, but don't worry, Chris. Nobody understands interfacial water. Yeah. that debate will continue to rage in the literature. Whitesides is one of the person actually stuck in the middle of that. But yeah, no, it's very strange. Water is incredibly strange. So what we do, everything we do is done in full explicit solvents. So I mean, when I started out, I first did computational biophysics, I guess 20 years ago, and even then we would still use, at least some of the water would be implicit. So we just have a dielectric constant of 80 for distant water. And eventually, when computers got good enough that we could actually have a full, extended system with full explicit water, guess what? The energy's changed wildly. So, you absolutely do need to have the full explicit solvent. And now, thanks to, Martin Karpus's group in Harvard, the charm force field, we have parameters for a very, very broad range of solvents. So from very, very low dielectric constant all the way out to water. So we can put, phospholipids, we can put peptides into a big box of any solvent. It could be acetone, it can be dimethylchlorine, dichloromethane, acetonitrile, water, whatever it is, and we can look at how the assemblies form, whether it's a membrane or say a micelle, or different types of structures form in those different solvents. And yeah, because you've got a different dielectric constant, you've got a different degree of buffering and mediating the hydrogen bonding between the molecules, you get completely different structures. So you can create brand new nanoarchitectures from exactly the same molecules just by changing the environment. And it's not just the solvent. You can also change the salt concentration. You can change the pH. You can add in, say, some metals in there, and guess what? Brand new structures again. So yeah, you can find wildly different structures. And finally, and it's only in the last few years we can do that. So rather than relying on starting with an X-ray structure or structure from spectroscopy, and then just doing our molecular dynamics, letting it evolve, letting it change over time, we can just have a random array of molecules in a particular environment and essentially press play on the computer. And over time, they will start to see each other. They will start to see each other through the environment, start to try different orientations, head-to-tail orientations, head-to-head orientations, and over time then build up that complexity. But they are still challenging calculations. We need very, very big computers to do that from scratch. But it's becoming more amenable to us.
Yeah, that is quite amazing. And then in context of nanoelectronics, and also Johan already alluded to that a little bit, and said how important the dynamics and the movements are. Is it now also possible, or are people working on it to then also follow the changes in electronic structure in real time, the changes of electronic structure of the system?
Yeah, so if you look at, say, some experimental work in spectroscopy where people, Harry Van de Sant does stuff like that. So you actually try to track the different vibrational states, different conformational energies, but they tend to be still in single molecule junctions. So they're done at close to 0 Kelvin, ultra high vacuum. So the types of systems that we're interested in, the large area arrays done in ambient, usually that are more amenable to integration into devices. No, that hasn't been done actually. It's quite difficult because you'd have to calculate the vibrational response in a very, very large area of film. which is still very, very challenging. Actually, people tend to do that even in very high impact papers. Even the best state-of-the-art papers tend to be still, you know, an isolated gas phase dimer or something. There's still a bit of work to be done to do that. So, you know, Pierre Cazet in my group, so he's one of our main coders. So he's done a lot of work in actually developing classical models, which are sophisticated enough to do that. So you can get those vibrational states without actually calculating all the time the full electronic structure, the full quantum mechanics from that. So yeah, I would say there's efforts being made to do that from a classical model. If you've got good enough quantum mechanics behind it in the force field, you should be able to get reliable vibrational states and relate them then to real-time, you know, in situ spectroscopy.
Yeah, no, wonderful. So I really enjoyed your talk. I really enjoyed the discussions. Are there any questions or no? Then I think it is my pleasure to hand over this well-deserved certificate to you, Damien. The certificate will also be emailed to you, and then of course you can put it on the wall of fame.
I will. I will.
Yeah, no, congratulations. Thanks a lot.
Yep. Thank you, Chris. Thank you to the organizers. Thank you to Alice. Thank you to the panel. It's been really great. Thank you. I've really enjoyed it.
Yeah, thank you, Damien.
Thank you.
Okay, and looking forward to the next one. Thanks, guys.
Yeah, and then before I'll close up, let me have a few final announcements. Well, next week, Friday, we're not going to have the usual scientific talk. Instead, we're going to have Rising Stars of Light before faculty track. So we're going to have 7 speakers that are all listed here. So tune in for next week. And then I also would like already to make an advertisement, because next year in Davos, in 2024, 11 to 12 of July, we're going to have an iCANX live event. We're going to have a whole bunch of fantastic plenary speakers and other speakers, but this will be the first live event for iCANX. So then you can meet Alice, then I will also be there, other board members will be there. You can see each other all in real life. So I'm very much excited about that happening. So herewith I would conclude today's episode of iCANX Talks, and I hope to see you all next week again. And I wish you all a very good weekend ahead. Bye-bye.
Bye.
Bye.
Great.
不再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞。不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can。没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失 失败，放弃或跟上，努力才是真的方向。I can，没有什么可以阻挡心中无限的力量。I can，你也能够像我一样飞越最高山岗。I can，没有什么可以阻挡心中无限的